I am Dr. Rajiv Mishra from IIT Patna. The topic of today's lecture is Introduction to Federated Learning at IoT Edge. In this lecture, we will cover the following details. First is we will show the current IoT scenarios, then why there is a need to shift from centralized machine learning training to decentralized machine learning training of an IoT data. Then we will also discuss the concepts in this domain which is called distributed machine learning, that is a federated learning concepts. Then we will also cover several challenges of federated learning. Besides this, we will also cover few applications of federated learning which is at the use. Let us talk about the current IoT scenario. So, there is an explosion of IoT market, and various forecasting agencies such as McKinsey reported $11.1 trillion market value of an IoT use cases by 2025. Bosch company, who is working with IoT technologies, so they are expecting that 14 billion connected devices will be there. Cisco is expecting that 5 billion connected devices. Gartner also projected 309 billion IoT supplier revenues, and IDC is a forecasting company also suggested that 7.1 trillion IoT solution revenue will be exploding this IoT market. So, this growth, if you see about the global IoT market size, that is continuously growing over 2017, that was 24% of the US dollar size. Now it has gone in 2020, that is 38.3%, and that is ever growing if you go by this forecasting agencies like McKinsey. Now there is a deluge of data, that is overwhelm of that particular data which is observed in 2020. So, why this so much of data is being observed, that is in this IoT scenario. So, what we are going to see is 1.5 gigabytes of traffic per day is originated because of this IoT growth from an average internet user. Similarly, with the advent of smart hospitals, this particular deluge of data is 300 gigabytes per day. So, deluge of data is also in the domain which is expected called self driving car, that is 4000 gigabytes per day. Radars also are significantly adding this particular data traffic. Connected aircrafts, connected factories are also able to generate so much of particular data, and this all is seen as deluge of data that is observed 2020 and also being forecasted as the soaring revenues in an IoT market by 2025. So, let us see what are the key players, what are the key technologies which are also shifting in this particular line to tap this or facilitate this explosion of an IoT market, and also to deal with deluge of data. So, the first aspect which we will discuss in this lecture is that we are going to shift from centralized data to decentralized data. Let us understand a particular scenario in this shift. So, the standard setting in machine learning considers centralized data processed in a tightly integrated system. That is what we have so far seen, and that was happening in the cloud, that is AI in the cloud, and therefore, the entire data set has to be moved to the cloud for performing the machine learning. So, therefore, this standard setting in machine learning considers the centralized data set processed in a tightly integrated system, that is it requires, that is AI requires so far centralized data. But in the real world, this is often decentralized across many IoT devices, because the data is generated not at one place, but through various devices which are separated or which are geographically distributed across the globe, and therefore, this particular real world data is decentralized across the globe, and that is being generated by an IoT scenario or IoT devices. Now, sending the entire data to the cloud for centralized AI or the machine learning may become too costly to support or to continue this scale which is being projected by an IoT market. For example, the new kind of innovation wave which is in the form of in IoT, which is in the form of self-driving car, is expected to generate several trillion bytes of data per day. Similarly, new wireless devices also have the limited bandwidth and the power to transfer that particular data. So, one side of this particular scenario is ever growing number of devices, that is IoT devices connecting to the cloud through internet, whereas these wireless communication and these devices sometimes have the limited bandwidth or the power. So, data may be considered also sometimes too sensitive, such as medical reports, or let us say mobile data, which is highly personalized data. Now, if you see this growing public awareness and the regulations on data privacy, it is not easy to transfer the data, yet you are going to protect or preserve the privacy without the consent of the people. So, therefore, to perform these artificial intelligence or machine learning, you have to keep the control of the data and can give a competitive edge in the business research if this particular protection is ensured. So, therefore, protection will build the trust of the people's data, and yet you are going to use that particular data with a control and now foster the research and the business in this particular scenario. So, here the scenario is shown over here is that there are several IoT devices which are generating the data and often sending to the cloud, that is called the centralized data. But this particular scenario is called centralized data, and centralized data is being consumed and processed in a place of a cloud, that is called data center, that we have already covered. Now, but if you see the real world devices such as connected cars, hospitals, smart hospitals, government organizations, mobile phones carried by the people, and so on, various other factories where IoT devices are embedded, or computers. So, these particular devices, they are IoT market, they are generating the data not at one place, but from different places, that is that particular data is decentralized data. Now, how do you fill the gap? So, one way for centralized data is to ship all the data towards the cloud, which requires the lot of bandwidth. Instead, what you can do is you can stop shipping the data and perform the artificial intelligence or machine learning on a decentralized data, thereby, so data need not to move heavily on the internet, but will be stored close by those devices, that is the source, and this is called the edge or a network edge. So, that means the data has to be stored and processed at the network edge, and this becomes the concept of edge computing. So, decentralized data is a need, and this particular model of decentralization of that particular data for performing various analytics and applying the machine learning is requires a technology which is called the edge computing. Now, let us see in the machine learning paradigm how this distributed data we are going to use that particular model for machine learning. So, that kind of machine learning is called a distributed machine learning, in contrast to the centralized data and performing the machine learning. So, if the data is distributed and if you are doing the machine learning with a distributed data, then this becomes a distributed machine learning. We will see one type of machine learning that is in this particular domain. That machine learning, which is a distributed machine learning, is done through a very popular model of a machine learning that is called federated learning. So, federated learning algorithms and the protocols both we are going to discuss in this particular lecture. So, the topic of this particular lecture is going to be a very important development towards edge computing. So, let us see the details about the federated learning, which is nothing but a concept of a distributed machine learning. So, 2016 the term federated learning is first coined by the company, that is the Google, where the researchers they have published more than 1000 papers in federated learning of their contributions. Now, we have already seen some of the real world gadgets and the deployments by the companies and researchers for large scale IoT devices using that distributed machine learning concept and also called as federated learning. So, several open source libraries therefore are also under the development. Lot of resources are available in this particular area, that is called a federated learning. PySwift, TensorFlow federated, then Flower and so on. There are many other platforms for federated learning platforms are available. These platforms will provide the customers to bring their federated learning algorithm and run on a particular scenario which is called a distributed data. So, these particular federated learning platforms they provide the protocols, that is federated learning protocols. So, these protocols we are going to cover in this particular lecture session, and also we will cover one very important federated learning algorithms, and these particular platforms which are available as open source, that you can refer and see that particular libraries. Due to the scope, that due to the time constraint, we are not going to cover that platforms. So, we are going to cover federated learning algorithms and federated learning protocols. So, federated learning is highly multidisciplinary. It involves machine learning, numerical optimization, privacy, security, network systems and hardware. So, we are going to cover these aspects of federated learning, which is becoming multidisciplinary and very popular. So, some aspects from this particular angle we are going to cover. So, federated learning means that performing the machine learning with the federated with a decentralized data. So, federated learning aims to collectively train the machine learning models while keeping the data decentralized. That means, data will remain wherever it is generated or it is kept, to the satisfaction of privacy and the locality or localization. Data need not have to move away from that premise to the cloud for performing this distributed learning, and that particular kind of concept is called federated learning. So, federated learning technologies aim to collectively train the machine learning model while keeping the data decentralized. This is a very important development. We will see how that is possible using federated learning. Federated learning also enable the devices to learn from each other, that is, the machine learning is brought very close by. So then next thing is that federated learning, in federated learning a network of nodes or all the nodes with their own central server, but instead of sharing the data with the central server, we will share the model. We do not send the data from one node to the server, instead we will only send the model, and that is acceptable in this particular learning parlance. So, take this example, here you have one end that is called connected edge devices. Then these edge devices are having that model of decentralized data. Now you can apply these machine learning models, that is AI, using federated learning to derive the intelligence from the device data without moving the data to the cloud. So that particular concept of an AI called a federated learning will improve the performance at the edge. So the edge, that means that part of training or machine learning which earlier used to happen at the cloud now will be performed at the edge where these devices are operating. So take this particular example, the nodes are the edge devices where the IoT is connected to or is being supported. Now these nodes are given, they are the edge nodes very close by to that particular IoT, maybe in the same premise. So it is in the same premise, these IoT and these edge nodes. So IoT will generate the data and it is available at the edge nodes. Now if you bring the machine learning model, if you can bring the machine learning algorithm and train the model using this IoT data at the node itself, that is at the edge nodes, and then the trained model will be sent to the servers and server will do the aggregation of these trained model. So that is the architecture of federated learning, that is about the distributed data. How that is all done? Through the federated learning that we are going to see. So therefore federated learning is the federated learning will give the way or the concepts to the edge computing. So with the help of federated learning, the edge computing is becoming more mature. Let us go ahead and see the growth. Now to do this aggregated learning or learning at the nodes and aggregated learning at the server, so that learning part is done through a particular process or the algorithm, and that is popularly known as gradient descent. So you can see on one side you have the machine learning algorithm and the other side you have the data. So data and machine learning both cannot be used to train the system. For that you require a glue, you require another technique, and that is called the gradient descent. So using gradient descent, and you can use the data, or the gradient descent will use the data and train the machine learning model. So training has to be happen using an algorithm that is called a gradient descent. Let us understand about that procedure. So gradient descent procedure starts off with the initial values of a coefficients for the function, and this could be initialized to 0 or a very small random number. Let us assume that this particular coefficient is initialized to 0, that becomes the equation number 1. Then the cost of coefficient is evaluated by plugging them in a function and calculating the cost. So cost of this particular coefficient is a function. So either that will be computed with the help of a function, or it will be evaluated applying this particular function of that coefficients, and that will calculate the cost. Now, we need to know the slope. Gradient descent works, descent means it will go to an optimal value, that means it has to find out a convex optimization. For that it has to now work around the slope, so that you know the direction or the sign of moving the coefficient values in order to get the lower cost. So, this cost function has to be reduced to the minimal. So, how to go ahead to find out the optimal values over the iterations? So, this procedure is well defined using the method called gradient descent. So, gradient descent will use the derivative of that particular cost, and that becomes the delta. So, delta is nothing but the derivative of the cost function, which I have already told that it is derived out of the coefficient by applying a function, and that becomes a cost of cost function. So, the cost and the derivative of that particular cost will become the delta. So, it has to be differentiable. So, we can now update the coefficient values, and the learning rate parameter we have to also fix, that is called the alpha, which is specified by the designers. So, learning rate parameter, which is called the alpha, must be specified, that controls how much coefficient can change on each update. So, the coefficient, so the fourth equation using 1, 2, 3, it becomes the update of coefficients. So, coefficient will be updated by plugging the learning rate that we have already explained, and the delta which we have calculated out of step number 3. So, this process of update is done in one iteration. So, the process is repeated until the cost of this coefficient becomes 0 or very close to 0. So, it does require to know the gradient of your cost function or a function you are optimizing. So, the gradient descent algorithm, let us briefly cover it. So, gradient descent is the most basic but most used optimization algorithm. So, gradient descent is an optimization algorithm. So, it's used heavily in the linear regression and the classification activities. So, backpropagation in the neural network, the federated learning is also uses this gradient descent, whether it is a backpropagation in the neural network and federated learning both uses gradient descent as an optimization algorithm. So, what are we optimizing? We are optimizing the learning of a model. So, gradient descent is the first order optimization algorithm which is dependent upon the first order derivatives of a loss function. So, it calculates that which way the weight should be altered so that the function can reach the minima, and through the backpropagation the loss is transferred from one layer to another layer, and the model's parameter also known as the weights are modified depending upon the losses, so that losses can be minimized. Therefore, the algorithm can be specified over executing several iterations, and it can be very briefly explained using only one equation. So, again that equation we have already explained. So, this is the coefficient is updated with the help of learning rate and the derivative of the loss function. So, the advantages we have seen in this optimization algorithm, which requires to train with the decentralized data. We are going to see the protocol of federated learning, how that is using the gradient descent for this method. So, advantages is that it is easy to compute, easy to implement, easy to understand. Now, once having understood this gradient descent optimization algorithm, then we have to go for the next step to understand the entire federated learning algorithm. So, the devices train the generic neural network model using gradient descent algorithm, and thereby the trained weights are sent to the server. The server then takes the average of all the updates to return the final weights. So, let us see, before we go and discuss the federated learning algorithm, let us see about this edge computing with the help of federated learning to perform the machine learning. So, federated learning is a category of machine learning algorithm which moves the processing over the edge nodes. What do you mean by moving the processing over the edge nodes? So, earlier the processing in the centralized data. So, that means moving the processing to the clients, to the edge nodes, so that the client's data can be maintained there itself without movement. So, this gives a birth to the decentralized distributed data, performing the machine learning on distributed data, or also you can say it is a distributed machine learning. So, if you are performing the machine learning on those distributed nodes, they are called edge nodes, because they will be able to perform the computation. This approach is not only a precise algorithm, but also a design of a framework for edge computing that we will explain. Now, federated learning is a method of machine learning that trains the machine learning model with the local data samples distributed over multiple edge devices or the server without exchange of this particular data, and this term federated learning was coined by McMahon in 2016. So, federated learning distributes the deep learning by eliminating the necessity of pooling the data in one single place. So, federated learning, the model is trained at different sites in numerous iterations. This method stands in contrary to the conventional techniques of a machine learning, where data set is transferred to a single server, that is the cloud, and to a more traditional decentralized techniques that undertake that local data set. So, for example, these are all IoT devices, they are sending the data to the edge nodes. Now, with the federated learning, which is being coordinated learning, is being performed where the data is, and then it will send only the parameters, not the data. So, data will stay wherever it is being generated, and it will be sent to the centralized server, that is which is running the federated learning server for model aggregation. So, it will do the model aggregation. This is the formula for model aggregation, and then this particular server will again push back these particular updates of the aggregated model parameters. So, therefore, let us see what are the building blocks or governing equations or governing algorithms which will perform the model training in a decentralized way at the edge nodes, that is wherever this IoT is functioning. So, thereby in the model training you have to find a function for that model training. So, given a training data set which comprises of n input and output pair, let us say that xi and yi, and which belongs to a domain of that data set, and the goal of this deep learning model training is to find a set of parameter w such that the average of p of yi becomes maximized given an xi. So, this means that if you are given a input sample of a data set, that is let us say x0 and y0, the goal of the deep learning model training is to find a set of parameter w to maximize the probability of outputting y0 giving x0. So, given the input data set let us say this is the trained data set or it is labeled data set. This will be the example of supervised learning. So, this particular supervised learning will train the model and it will collect the deep learning model training parameters such as W with the scope that it will maximize the probability of outputting Y0. Means that what are the parameters when your model is perfectly trained with the supervised learning of a data set. Therefore, you have to find a particular probability function which will maximize the value of y given xi, and that is being expressed the maximization, that is an optimization in the model training process. So, that means you want to maximize the probability of maximum values of yi learned given the value of x. So, which is equivalent to minimizing the error. So, the error function is written in this following manner, that is minus log of p of yi given the values of x and w. So, this basic component for the loss function is given with a sample data set, and let fw be the function of these particular w, and thereby it will be easy to calculate the loss function by applying the log values to it and to minimize it. So, deep learning model training in this particular method, using this method you are given an input sample x0 y0, and the goal of the deep learning model training is to find the set of parameter w to maximize the probability of outputting y0 given x0. So, let us see that aggregation, how the server does this aggregation of the models which are trained at different decentralized data sites, and then what is the governing algorithm which will do this aggregation method. So, very important algorithm is called federated averaging. Fed average is popularly known as, and it has given the lot of use for federated learning using this particular algorithm. So, algorithm goes like this. This algorithm is called federated averaging. This particular algorithm has two parts, one is called the server, the other is called the clients. So, clients will perform using federated averaging, which is a particular algorithm of performing the federated learning. So, federated learning algorithm called federated averaging comprises of two components. One will run at the client, client means all the devices will be running this particular algorithm called client update. So, what it will do, it will split the pk into the batches of size b, and for each epoch I from 1 to e it will perform in the batches, and you know that these iterations what we have discussed in the previous slide is that coefficients or the parameters, weights we call it, with the learning rate and the derivative, this particular things will be returned to the server after being computed this weight w at the client's end. Server what it will do, initially when none of the clients have sent the data or weights back, so it has to initialize with weight 0, and for every round or for every iterations what it will do, it will maximize this ck and 1, and it will also search the random set of m clients, and then it will update the clients. Client update when comes here in the server, it will be then perform the averaging of these weights, and this is called the federated learning, and these newly calculated weights are being again fed back to the client. Let us understand. So, at the first, the model is randomly initialized on the central server that we have already shown. So, at first the model is randomly initialized on the central server, then for each round T a random set of clients are chosen, not all the clients. So, some k clients are randomly chosen by the server and each client performs local gradient descent steps. So, here the local gradient steps are being executed on every edge nodes. So, they are at the edge. So, edge nodes will execute the gradient descent steps, and then the computed weight, that is W, is sent to the server, and the server will aggregate the model parameters submitted by the client here. So, the client update will submit its weight and then it will be aggregated and then updated and so on. So, this is a very simple way of a federated learning. So, federated learning will select randomly the k clients. So, not all the clients, randomly k clients are being chosen maybe, and B is the local batch size which is required by the clients or the edge nodes, and E is the number of local epochs, and there is a learning rate. These parameters are needed. Now, let us see implementation experience of a federated learning with IID data. So, in federated learning, each client trains its model in a decentralized way. In other words, the model training process carried out separately at each client, that we have explained in the previous slides. Only the learned model parameters are sent to the server to aggregate and feed the aggregated main model back. Then the trusted server will send back the aggregated main model back to these particular client, and this process is continued. Now, we will see an experience of this federated learning implementation with IID data. The full form of IID is independent and identically distributed. So, independent and identically distributed data, IID data implementation is shown here in this particular example. So, we will see that how the parameters of hundreds of different models that are running on different node can be combined using federated averaging algorithm method, which we have seen one type of federated learning algorithm which I have already discussed in the previous slides. So, whether this model, that is federated averaging based training, will give the reasonable results or not. So, let us see this experience. So, this particular data set, let us see that it is a public data set which is widely used, called MNIST data set. It is a handwritten digits. So, this data set will contain the images in the gray scale of handwritten digit from 0 to 9. So, let us see how you can build the same classifiers which centralized learning also has already done this experience. So, MNIST data set does not contain each label equally, therefore, to fulfill the independent and identically distributed requirement, the data set was grouped, shuffled and then distributed, so that each node contains an equal number of each label. So, this is very important. So, the very basic requirement of independent and identically distributed is to group them, shuffle them and then distribute, so that each node contains an almost equal number of each label. So, here you can use a very simple 2-layer model for the classification process and applying the federated learning. Now, these parameters of the main model and the parameters of all the local models are randomly initialized, that we have already explained. So, these parameters will be different from each, and the main model will send its parameter to the nodes before the training of a local data begins. Nodes start to train their local models over their own data by using these parameters, and each node updates its parameter while training its own model, and after the training process is complete, the node sends its parameter to the main model. Main model takes the average of these parameters and set them its new weight and passes back to the nodes for the next iteration. The above flow is for one iteration, and this iteration can be repeated over and over to improve the main model. So, what we have seen is that, let us see an important comparison, that if you use the same data set in a deep learning model for the classification purpose, the accuracy of the centralized model in a similar implementation is giving 98% accuracy in a centralized model. What about here in federated learning using federated average? Accuracy is obtained 85% and can be improved up to 94%. So, you can see that you can achieve similar accuracy, almost similar accuracy in this distributed manner, that is using federated learning, without even sending the data to the central cloud. So, this particular development is quite serious and long lasting, in the sense that it will join the wave of innovation for IoT use cases and the growth using the edge computing. Now, let us see some more use cases of these federated learning. So, you might be using the Apple mobile phone, and Apple mobile phone is running a voice assistant called Siri. That Siri is now using your personalized data to optimize your phone configurations without hoovering up the data. So, your data protection is there, still it can use your data which is staying still in the mobile phone, but training the model with the help of federated learning. So, the tech giant like Apple is using privacy preserving machine learning to improve the voice assistant, that is Siri, while keeping your data on your phone. So, data is not moving, yet that particular voice assistant Siri will be now learning with your data which is there in your mobile phone. It relies primarily on the technique called federated learning that we have already explained. So, it allows the Apple to train different copies of the speaker recognition model across the user's devices using only the audio data available locally. So, Siri is the perfect example how the Apple runs a privacy preserving AI, that is in the form of voice powered assistant, is designed for continual at the edge improvement. So, this it sends the data, it sends just the updated models back to the server, not the data. In this manner, the raw audios of the users Siri request never leaves the iPhone or iPad, but the assistant continuously get better at identifying the right speaker, called differential privacy, to add further layer of protection. So, the technique injects a small amount of noise in the local machine learning model, and additional steps makes it difficult for malicious actor to reverse engineer the original data from the trained model. So, those kind of privacy issues are already taken care in the federated learning. So, federated learning model training protocol, let us go ahead and see. So, we have so far seen the federated learning algorithm and federated learning optimization algorithm, that is called gradient descent. We have also seen one use case of a federated learning, that is in the form of Apple's Siri, how that is being learning without moving the data, and that is called machine learning or privacy preserving machine learning, that is using the federated learning. So, federated learning protocol, let us see how all these steps are done. Let us see about the training. So, in the training there are nodes, these nodes are having connected with the connected devices, and let us say that you have a cluster of 4 IoT devices, and there is one central server. In this example, you have one central server plus you have 4 IoT clusters, node cluster. So, there is one central server, and initially it is having untrained model, and we will send the copy of this untrained model to each node, and each node will receive the copy of that model. This is the step number 1. So, let us see how the training will happen when the server is sending the model, that is untrained model, to the nodes. All the nodes in the network has untrained model that is received by the servers. So, in the next step we are taking the data from each node. By taking the data, it does not mean that we are sharing the data to anyone else other than that node. So, every node has its own data based on which is going to train a model. So, all this is called the distributed data. Plus untrained model. So, each node is training the model to fit the data and that they have, and it will train the model as according to its data. So, it will train the model. So, this is the picture of the model which you derive, that is in the form of W, which we have seen in the federated averaging algorithm. So, now the server and will send that this particular trained model, not the data, to the server. Now, the server will combine, that is also called aggregation, aggregate the model received from each node by taking the average of all the model receives from the nodes. The server will train the central model with this model, which is now trained by aggregating the model from each node. It captures the pattern in the training data on all the nodes, it is aggregated. Once the model is aggregated, the server will send the copy of the updated model back to the nodes, and everything is being achieved at the node. So, no data sharing in this particular process of learning is done in the federated learning, means that privacy preservation and also very less communication overhead is seen, yet the accuracy is almost similar to the centralized machine learning we have so far seen in this particular implementation experience. So, federated learning challenges, let us see that. So, these are the following challenges. Will have the system's heterogeneity, the size of the data varies from different nodes, computational power also varies from different nodes at the client's end. Network stability is also one of the issues, and local solvers and learning rate, these are all different parameters which brings up the heterogeneity. So, federated learning with all such systems heterogeneity becomes a challenge, and also an expensive communication, that is communication in the network can be slower than the local communication by the orders of the magnitude. Now further challenges is to deal with the non-IID data. IID data we have seen, that is independent and identical distributed. So learning from non-IoT data is difficult and slow. Why? Because each IoT device needs the model to go in a particular direction. So if the data distributions are very different, learning a single model which performs well for all the IoT devices may require a very large number of parameters in that case. So this is another challenge to deal with the non-IID data. Another direction is to deal with is to lift the requirement that the learned model should be the same for all the devices. So instead we can also allow IoT clients K, not all K, to learn a personalized model and so on. There are various other, but it is a challenging to deal with non-IID data. So privacy preserving, that is machine learning models are susceptible to various attacks on data privacy and the membership inference attacks, reconstruction and attacks, and federated learning offers additional attack surfaces. Data distribution, so key difference with the distributed learning is the data distribution. In a distributed learning, data is centrally stored, that is in the data center. The main goal is to train faster and we control how the data is distributed across the workers. So additional challenges in the federated learning is to enforce these privacy constraints, dealing with possibly limited reliable available participants and achieving robustness against the malicious parties. When to apply the federated learning? Whenever the data privacy is very essential, for example, the mobile phone data is a personal data, and if you want to use the data for training, then that is the only way, that is privacy preserving machine learning is called the federated learning. Otherwise it is not possible to pull the data from all the mobile phones to the cloud and do the training. So learning or a training is only way, that is called federated learning, to perform in this kind of scenario of a mobile data which contains the personal data. Bandwidth and the power consumption are also of the concern. Then also federated learning is quite useful. Why? Because it does not require the huge bandwidth to send the data, but only a little bandwidth is required to send the trained model. Power consumptions also are of concern. Then federated learning is applied. High cost of data transfer, if it is there, then using federated learning you can reduce the cost of the data transfer, because data transfer is not required while using the federated learning. Let us see when you are not using the federated learning, what are the scenarios. When more data won't improve your model, construct a learning cure, then go for the centralized one. When additional data is uncorrelated, so that means it requires IID data. If it is non-IID, then also this particular federated learning will not be applicable. Performance is already at the ceiling. There are various federated learning applications, such as in the industrial IoT, predictive maintenance is a great opportunity. Mobile phones, healthcare, wearables, drug discovery, enterprise or corporate ITs. Let us summarize this particular lecture. We have seen the market trends for IoT use cases. So IoT market is being predicted by different forecasting agencies to grow by 2025 several folds. Therefore lot of opportunity is there for edge computing and privacy preserving machine learning to tap this or to join this wave of innovation. So why decentralized training is important, that we have covered here in this lecture. We have also understood the federated learning concepts, and we have also shown various issues involved in the federated learning, when to use, when not to use the federated learning, and federated learning use cases for IoT and for mobile phone we have already seen. With this, let us conclude this lecture. Thank you very much. Thank you.